Hi, in this video we are going to discuss on topic tutorial 14, gravitational potential and potential energy. Okay, so we read the question. The first question, the mass of a planet is 5.0 times 10 to the power of 24 kilogram and its radius is 6 times 10 to the power of 8 meter. So what is the energy required to bring a mass of 2 kilogram from the surface of the planet to outer surface? So this means we are going to find the work done. So the work done is the change in energy. Okay, the energy required to bring a mass from the surface of the planet to outer space. Okay, we use the work energy theorem. Okay, now if you want, this is the diagram. Okay, to imagine what happened. Okay, so this is the mass that we are going to bring to the outer surface. So the distance is very far, so that means the energy at the infinity will be 0. So the energy at the surface of the earth is equals to the gravitation. We are going to use the gravitational energy on the surface of the earth. Okay, so energy required equals to change in potential energy. So at the final, the gravitational potential energy will be 0 because at the outer surface and it's very far away from the planet. Okay, so the U initial, U final first, so is 0. So U initial will be using the formula negative Gm over R, right? Because on the surface of the earth. Okay, so negative is plus. So the G value is 6.67 times 10 to the power of negative 11. M of the object is 5 times 10 to the power of 24. Oh, this is mass of the planet. Okay, then the mass of the object is 2 kilogram, and the distance, the radius of the planet is 6 times 10 to the power of 8. So we get the energy required is 1.11 times 10 to the power of 6 joule. Okay, so that's question number 1. Okay, next we go to question number 2. Okay, use the data shown in the figure to estimate the resultant gravitational field strength at the position of the moon. Mass of the earth is given 6 times 10 to the power of 24 kilogram. Mass of the sun is 2 times 10 to the power of 30 kilogram. And the gravitational potential constant is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Okay, so the distance of the earth to the moon is 3.9 times 10 over 8 meter. And the distance between earth and sun is 1.5 times 10 to the power of 11 meter. Okay, so we are going to find, go back to the question. So we are going to find the resultant gravitational field strength. Okay, resultant gravitational field strength. So we have 3 planets, 3 objects here. Okay, 2 planets and the moon. Okay, at the position, at the moon position, the direction of the gravitational field is towards the earth, because the earth is gravitational direction of gravitational force of the earth is radially towards the earth, and gravitational field is radially towards the earth. So therefore we draw the G direction from the moon is arrow towards to the earth. So we name this as G Earth. Okay, for the G Sun, moon attract to sun, so the field is towards the sun. So we name as GS. Okay, so there are 2 G gravitational field, right? Then GS is this way. We use vector and using the parallelogram method. So GS followed by GE. So this will be the resultant G. Okay, resultant gravitational field. Okay, so you to find the angle, so we can use a trigonometric ratio. Okay, trigonometric ratio, we can use tangent. Angle here is same as this angle because alternate angle. So we can use tangent theta equals to opposite 3.9 times 10 to the 8 divided by adjacent of the triangle 1.5 times 10 to the power of 11. So we get the angle here is very small, it's 0.149 degrees. Okay, so now the component x and component y of GE and GS. For GE, the component is for along x will be 0 because it vertically downward. So it has only component y, which is we use the formula gm over r squared. So the g value is 6.67 times 10 to the power of negative 11, and the mass of the moon is 6 times 10 to the power of 24. Also, this is the mass of the earth because the field is from the earth. The moon experience the field gravitational field for the earth. So this is mass of the earth. Okay, divided by distance 3.9 times 10 to the power of 8. Don't forget the square. Okay, so we calculate, we get negative 2.63 times 10 to the power of negative 3. Negative because it's downward. Okay, we put negative sign. Okay, we do the same for G sun. So G sun, gravitational field of the sun, the component along x will be to the right, okay, which is gs cos theta, and then the component along y is gs sin theta. Okay, so for gs, we use the formula gm over r squared. Okay, so the g gravitational field is 6.67, that gravitational constant is 6.67 times 10 to the power of negative 11, and the mass and the gs is cos gs 2 times 10 to the power of 30, the mass of the sun, because this one comes from the sun. So the formula gm over r comes from the mass of the sun. Don't forget the cos theta, just now we calculate 0.149. Okay, the distance we use Pythagoras theorem. The distance moon to the sun, we use Pythagoras theorem. So we get 1.5 times 10 to the power of 11. Why? Because this is very far, so the angle is very small, and even if we use Pythagoras theorem, so we will still get the same 1.5 times 10 to the power of 11. Okay, so even if you use Pythagoras theorem, you still get 1.5 times 10 to the power of 11. I repeat again, why the answer is the same, because the angle is very small. So we can assume that this is parallel to the distance between a sun. Okay, so now we substitute the value into here, the table. So 5.93 times 10 to the power of negative 3. And it is positive because to the left, to the right, okay, because the s cos theta is to the right. And then gs sin theta, we use the same formula gm over r squared. Okay, so we substitute the g and the mass of the sun, sine 0.149, and the distance 1.5 times 10 to the power of 11. Okay, so the answer is negative 1.54 times 10 to the power of negative 5, because it's downward direction. Gs sin theta is downward direction. Okay, so now we calculate the total of GE and G sun. So the total, this one will be 5.93 times 10 to the power of negative 3. And these two, when we total up, we get a negative 2.65 times 10 to the power of negative 3. Okay, so now from this total, we can use Pythagoras theorem to find the resultant. Okay, so 5.93 times 10 to the power of negative 3 is horizontal, okay, along x. G total along x, and G total along y is negative 2 downward, so we draw arrow downward to represent negative 2.65 times 10 to the power of -3. Okay, so the resultant will be in this direction, and the value you can calculate using Pythagoras theorem. So the square root of this x squared plus y squared, so we get 6.49 times 10 to the power of -3 Newton per kilogram. So this is the resultant gravitational field. Okay, on the measured on the moon. So the direction you can use trigonometric ratio. So this name as phi, because just now we use theta, so we use a different symbol for the angle here. So opposite is 2.65 times 10 to the -3 divided by adjacent to the angle here is 5.93 times 10 to the power of -3. So the psi is 24 degrees. Okay, measured from OX here. Okay, so I forgot to put the angle here, so I can draw there. So this is the angle, this angle, right? Okay, this angle. Okay, now we get we have answered the question. Okay, you can also use 66 degrees, because the vertical angle, the right angle here 90 degrees minus 24, we get 66 degrees. So either one you choose to mention the direction for gravitational field resultant. Okay, now we go to question 3. A body of mass m at the surface of the earth is brought to a point a distance to r. R is radius of the earth, from the center of the earth. So expressed in terms of m, the mass of the earth, r and g, the universal gravitational constant. And then the gravitational potential, and second, the gravitational potential energy of the body at a distance to r from the center of the earth. Okay. Next question is find the change in the gravitational potential energy of the body. And then has the gravitational potential energy of the body increase or decrease? So we do question A first. We are going to express in terms of M, R, and G. For the universal gravitational constant is brought from the center. We are going to express the gravitational potential and then gravitational potential energy. Okay, for gravitational potential, okay, the distance is 2r. So this is radius, and then double the radius will be somewhere here. So the distance 2r is measured from the center of the Earth. Okay, so that's the distance. That's the gravitational potential that we are going to derive. Okay, so what is the gravitational potential? So let's say we use symbol V. So gravitational potential, the formula is gravitational potential energy divided by M, or the work done from the energy theorem. Okay, so it's change in gravitational potential energy divided by the mass. Okay, so the mass is M, so already we use the symbol M given in the question. Okay, for the gravitational potential energy, okay, so we use negative GMM over 2R. So don't forget for formula you must put negative together. Bring along the negative sign together because the formula has negative there. Okay, so now we cancel the M and we get the answer negative GM over 2R. Okay, so we already answered the question. Because the questions want to express in terms of M, okay, already there, and then G, and then R. Okay, done. Next, we go to question 2. We are going to determine or express the gravitational potential energy, okay, at this point, at the distance to R. So for U, we use negative GMM over 2R that we used just now, this one, the formula of U. And all the given symbol for each term are already used here. Okay, so that's the answer. So we go to question B. So we are going to find change in gravitational potential energy. So change in gravitational potential energy is final minus initial potential energy. So the final will be at the at this point, okay. So at distance to r, so that's mean the formula is negative gmm over, so the distance is to r, okay. Then at the initial is at the on the surface, and on the surface, so negative formula negative gmm over r, so the r, the distance is we use radius of the planet, earth, okay, r. Okay, so now we simplify this. So we get negative minus here become plus. So this one means we double this 2 gmm over 2r. Positive 2 minus 1, we get positive value. So the answer is positive gmm over 2r. So if this is positive, so this means the gravitational potential energy is increased. So the gravitational potential energy increases. Okay, so because we get a positive value. Okay, then we go to question 4. Okay, a body is released from rest from a height to r from the surface of the earth. Derive a formula for the speed of the body when it reaches the earth's surface in terms of r, mass of the earth m, and the universal gravitational constant g. Okay, so next to imagine this, to imagine what happened, a body is released from to r. So somewhere up there, radius. So 2r means from the surface I mentioned here, the height. So height is 2r from the surface. So we double the r from the surface. So measured from the center will be 3r. Okay. So 2r and then plus r is 3r. So we use principle of conservation of energy. So principle of conservation of energy said that total of energy is equals to the total of energy at final, at two position, at initial and at final. So when we bring kinetic energy to one side and potential energy to one side, so we get change in kinetic energy equals to change in potential energy. Okay, so now we choose the either one, we can choose the change in kinetic energy. So we choose the gain in kinetic energy because it bring to this position. So that's mean the potential it means the gain in kinetic energy and equals to the loss in potential energy. Okay, so kinetic energy at initial at on the surface will be half mv squared minus 0. So at final 0 at final is at outer space, so that means 0. Okay, then loss in potential energy. So potential energy at the position here final distance is 2r, so we use formula gmm over 3r, right? Because distance is 3r. And then at the surface here initial will be gmm over r. Okay, gmm over r. Okay, so now we multiplied by 3, okay, top and bottom, so that we can minus top this 2. So negative minus minus become plus. So negative 1 plus 3 is positive 2. So we get 2 gmm over 3r. Okay, so cross multiply, cancel the m and we get v, and then cross multiply 2 to here. So we get square root of 4 gm over 3r. Okay, 4 gm over 3r. So this is the answer because the questions want speed in terms of r. Okay, already r there, m, okay, then g. Okay, so we have answered the question. Okay, question 5a, write the formula for the gravitational potential energy of a mass m on the surface of the earth in terms of r and radius of the earth m, the mass of the earth, and g, the universal gravitational constant, and b, deduce the formula for the speed of a meteorite when it strikes the surface of the earth. Okay, so how to imagine this? Okay, write the formula. The question only asks write the formula of the gravitational potential energy. So U equals to negative gmm over r. Okay? Okay, so on the surface, so the distance is r, radius of the earth. Okay, next we are going to find B. So we use principle of conservation of energy. So again, and same as question 4 just now. So we use gain in kinetic energy equals to loss in potential energy. So gain in kinetic energy will be half mv squared minus 0. Okay, because at the infinity, the kinetic energy will be 0 at initial with the speed speed v, so it's half mv squared for the kinetic energy. Okay, the loss in potential energy at the infinity will be 0. Okay, at initial on the surface of the earth is negative gmm over r. Okay, so now we rearrange the equation. We put as a subject, so we get square root of 2gm over r. Okay, so that's the answer. Okay, next we go to question 6. The figure below is the graph. Okay, v against x from the surface of a planet of radius 5.2 times 10 to the 6 meter. Okay, calculate the mass of the planet and the energy required to launch a rocket of mass 500 kg to a height of 600 kilometer. So if the rocket is launched with the energy you calculated in A2 above, what is the speed of the rocket at a height of 200 kilometer? So we do question A1, the mass of the planet. So at the there are two analyses can be made from the graph, which is gradient and the area under the graph. Another one is the y-intercept. So the y-intercept here means it's the on the surface of the earth, because this is x kilometer. So on the surface, mentioned here against the distance from the surface. So that means 0 means on the surface. This is the value. So it's speed is 5.6. 5 times 10 to 6 if we read from the y-intercept. So this is the v on the surface. So we can find the mass of the planet using this formula. V equals to negative gm over r. Okay, so the mass is cross multiply, we get vr over g. Okay? So the v is this one. Go back to the slide. Okay, so you substitute this v into here, and then the r are given here. Okay, then the g is the gravitational constant. Then you can calculate by yourself the answer. So this is the mass of the planet. Okay, next we go to A2. Okay, A2, the energy required to launch a rocket of mass 500 kilogram to a height of 600 kilometer. Okay, so from the graph here, the reading 600 meter. Okay, from the surface 0 to 600. So we read the V value. Okay, so V is gravitational potential. The gravitational potential given the reading here is negative 5.06. Okay, so on the surface just now is 5.65. So the U formula is negative gmm over r, and the relationship between the V, because we can read the delta change in V here. So cross multiply, we get U is V times M. From these two, you compare or use ratio method, you get U equals to Vm. Vm. So the V, you take the reading here, because from the surface to the 600 kilometer, so the change will be this, the gravitational potential V, the change in gravitational potential energy. So you substitute into here, and the mass that you calculate just now, mass of the object, not mass of the earth, mass the rocket of mass 500 kg. So you substitute 500 kg into here, and this delta V, so you get the answer. The answer is 2.95 times 10 to the power of 8. Okay, so this delta V, if we calculate, okay, 5.6 5.65, this here is 5.65 times 5.06 there. So you get the answer. Okay, next we go to question B. If the rocket is launched with the energy you calculate in A, Okay, we calculate already. Just now we get 2.95 times 10 to the power of 8 joules. So we use this energy. Okay, we use this energy. So we are going to find the speed of the rocket at height 200 kilometer. So we use the principle of conservation of energy. So total of energy will be kinetic energy plus potential energy. So at initial equals to the final. So the energy we calculate just now is 2.95 times 10 to the power 8. Okay, so the uh, kinetic energy, we use half mv squared, where we can find speed from here. And then potential energy, we read the reading from the graph, 0 to 200. So that's mean we can use vm, the relationship that we use just now in A2, in A2. Okay, so the reading here is 5.43. Okay, label in the question, the diagram already at 200. So the reading is 5.43. So at the y-intercept here on the surface is 5.65. So the change will be 5.65 times 5.43. Don't forget it's times 10 to the power 6. Okay, then times the 500 kg, the rocket as mass 200 kilogram. 500 kilograms, so we substitute into here, so we get the answer. Okay, so you can calculate there by yourself for the speed of the rocket. Okay, next we go to question 7. A body of mass m is at height h above the surface of the earth of mass m and radius r. So if h less or equals to r, such that term h over r of power greater than 1 can be neglected. So derive an expression for the gravitational potential energy u of the body in terms of m, h, m of mass of the earth, r, and then g gravitational constant. Okay, so at height h, so if we mention here height h above the surface, so it's not from the center, so it's from the surface of the earth. This is h. Okay, so the distance will be h plus r. So don't forget the distance must always be measured from the center of the earth. So the gravitational potential formula is negative gm m over r. So the distance is r plus h. Okay, don't make this mistake. When common mistake student makes is not measured distance from the center of the earth. So r plus h. And another one is must put the negative sign for the formula u. Okay, so we are going to write the in terms of this one h over r. So we can convert this to 1 plus h over r. So it's the same. Okay, we factor out r. So bracket we put 1 plus h over r. So these two is actually the same. So we just put in terms of h over r. Okay, so now we bring this up, so we get negative gm over r, so bracket 1 plus h over r to the power of negative 1. So this we use expansion. Okay, so this one it's become 1 minus h over r plus bracket h over r squared minus bracket h over r cubed plus dot dot dot. Okay, so you've learned these rules in the mathematics T. Okay. So the question asks to power greater. For the power greater, we can neglect it. So the power greater than 1 can be neglected. So the power square here, all this we can neglect. So we get the answer. Okay, I didn't do. So the answer is negative gm over r bracket 1 minus h over r only. So this the first two terms only, because we can neglect the rest of the answer here. Okay, so that's the answer. So now we go to last question 8. The radius of mass is 3.4 times 10 to the power of 6 meter, and the acceleration due to gravity on the surface of mass is 3.70 meter per second. So calculate the mass of the mass, the mean density of the mass, the mean density of the mass actually, and the gravitational potential on the surface of the mass. Okay, so this is radius of the mass and this is g on the mass. So we use gravitational potential force, gravitational force, which is gm over r squared, And on the surface, F is mg, then equals to gm over r squared, and the r is radius of the planet. So we cancel the m, so we get m cross multiply, so we get m equals to gr squared over g. Okay, so you substitute g value 3.7, and then radius of the mass 3.4 times 10 of 6, don't forget the square, and the g is gravitational constant, and the answer, the mass is 6.4 times 10 to the power of 23 kilogram. Okay, next, the density. So for the density, we can use mass over volume. So the mass calculated already. So the volume, we assume the mass planet is a spherical, a sphere shape. So we use formula volume 4 over 3 pi r cube. Okay, so you substitute this mass into the formula, and then 4 over 3 pi r. So radius of the mass 3.4 times 10 to the 6. And then don't forget cube. So we get the answer 3.9 times 10 to the power 3 kilogram per meter cube. Okay. So lastly is the gravitational potential on the surface. So symbol V, gravitational potential. So we can use negative Gm over R formula. Okay, so the G value is 6.67 times 10 to the power of negative 11. Mass of the planet, mass is 6.4 times 10 to the power of 23, and the radius. So we get the answer negative 1.3 times 10 to the power of 7 joule per kilogram. So this is the gravitational potential on the surface of the mass. So be careful with the gravitational potential. Another one is the gravitational potential energy. Okay, gravitational potential energy is U. Gravitational potential, we use symbol V. Okay. So that's the end of tutorial 14. Okay, bye-bye.